I'll have to open it. You've never used that?
No, you used it.
I'll start over.
Hello everyone, for coming for Books Bagels. Today we will have 3 short presentations followed by a moderated discussion. The audience participation is highly encouraged for this discussion. So my name is Kavan. I am at my last year of my PhD program at Mechanical Engineering and Mechanics Department. So I have been selected as a Vice President of the Graduate Student Association for Academic Affairs recently. The Graduate Student Association is pleased to welcome Dr. DiNardo, Senior Vice Provost of Academic Affairs, as the moderator for the 22nd Books Bagels program, which started on January 2012. Dr. DiNardo has been a crucial part of this program and is a strong advocate for graduate studies and interdisciplinary research at Drexel University. Dr. DiNardo, Professor of Physics, was appointed as the Vice Provost of Academic Affairs in October 2005. Prior to this appointment, he was appointed as Associate Dean of College of Art and Science. Dr. DiNardo has started his journey with the research here at Drexel. And after getting his Bachelor of Science from Drexel University, he attended the University of Pennsylvania at Physics Department to accomplish his PhD program. Afterwards, he joined IBM Research in New York City to pursue his research aims as a postdoc fellowship. Afterwards, he went back to the home, Drexel, and he was appointed as a tenure-track position professor at the Department of Physics. Since then, he has placed emphasis on research in the field of nanoscience and biophysics. Thank you, Dr. DiNardo.
Good afternoon. I'll just be brief right now, but I just want to welcome everyone to Books and Bagels. Which number is it? 22nd Books and Bagels. I also want to just make a couple of comments. We have 3 really exciting talks today, I think, that really, stress essentially what we've been trying to do with this series that's been so well led by the Graduate Studies Office and by the GSA. And in terms of the way we want to really proceed is to just try to appreciate a couple of different things. And I think the one piece that I certainly appreciate from meeting with the speakers is their breadth of knowledge and the fact that they are moving in very interdisciplinary areas. And so that's really a very interesting piece of things that we should be talking about and should be reflecting upon as our own research moves forward. The second part of this is, how does this fit into our own strategic initiatives within the university? And I think that, I'm hoping that all of you are somewhat familiar and conversant in how we're trying to pursue interdisciplinary research in an ever-increasing way at Drexel. And I think we have some very unique opportunities here to not only be able to pursue excellent research, but to be able to work across disciplines in a very smooth way. Many of you are already doing that, and I really applaud that. Within the strategic plan and within some of the directions that we're going, these 3 talks really do also sort of coalesce around areas of interdisciplinary areas of the university that are within our strategic goals for hiring and for pursuing more research. Broad areas: energy and the environment, computing, and health sciences and medicine. And so within this, I think you're going to hear from our 3 speakers elements of these, and I think they'll be presenting not only some elements of their own research, but beyond that, sort of how this really applies to their own personal growth, but also to the growth of knowledge, not only at Drexel University, but within the academy. So with that said, I want to start by introducing Sam Kennerly, who's a graduate actually from the physics department, so I have some affinity there. But basically, he will be speaking about some of the work that he's been doing in computational physics. Sam.
Thanks. While we're doing the button clicking, my name's Sam. I've been here about 6.8 years, and I just finished my thesis today and am turning it into the library. And the point of this talk is I had a specific math problem I had to solve. It was a stochastic differential equation on a sphere, and I've got some pictures of it, which I think you guys can see. Yeah, good, it works. And the whole point is the program that I wrote for it, the methods that I used, have a zillion applications, and I don't know the large majority of them, so I'm hoping you guys will, someone will look at it and say, oh, well, you can do that. And then you go to my website, and if you don't like my program, it's written to be real easy to hack, and it's got references to all the people who came up with all the hard parts. So the name of the topic is Geometric Numerical Integrators. That's a huge subject. I'm going to focus on just a small number of these things, but I thought that was a little catchier than the exponential midpoint calculation method as a title. So the type of problem that this software solves and that these methods were designed for is called an ordinary differential equation. If you're in the physics department, you're already supposed to know what that means, but not everyone could reasonably be expected to define that off the top of their head. So I tried to make a low jargon version, which is actually pretty difficult. So the simplest example, there's some number that describes the population of wolves in a forest or the position of a bowling ball or whatever. And it depends on some other number, which I'm going to call t in time, but mathematics doesn't care whether you call it time or something else. The font got a little messed up in some conversions here, but x dot is Newton's old notation for a time derivative. And if you don't know much of calculus, you can think of it as a rate of change, and you have a better intuition about it than you get in most textbooks. So an ordinary differential equation, I've written kind of a really simple example. Let's say I know x dot obeys some function or some rule that I can predict, but I don't know what x is. I want to find x. That's an ordinary differential equation. I want a function for x as a function of t. And if I know a value of x at some time, that's called an initial value problem. So numerical integrators were designed for initial value problems. I know where the bowling ball is. I know a differential equation for where it will be. Tell me where it will be at time t. The number you're predicting is called a dependent variable. The other one is called the independent variable, which I call time. And an ordinary differential equation means it's only got t rates of change in it. There's no other derivatives. For that, you have to ask the other people in my office. Partial differential equation. And of course, you can have multiple numbers you're tracking. Maybe it's the x, y, and z coordinates of a bird or something. And you can have higher order derivatives. There's a trick you can look up in textbooks. I've given you the keyword to search for if you want to see it on Wikipedia. Reduction of order lets you write any ordinary differential equation, ODEs, as their first order one, but you might need a whole bunch of variables, which I write a whole number for a vector. And if you use MATLAB or something, you can think of it as just a column of numbers. So that's the kind of problem I'm trying to solve. It comes up all over engineering and physics and biology and everything. If you can write an ODE in this form, I call it a generator equation, and that's an esoteric group theory reference, which I can get away with because my advisor is group theory. You have some column vector, and its time derivative is some matrix times itself. That's a generator equation. If you look at reduction of order, it'll tell you how to write any ordinary differential equation in this form. So the applications are, I have numbers, they change in time, I need to figure out what the numbers are. It's a pretty broad range of applications. I call it a generator equation because a group theorist might call it called G, this matrix, an infinitesimal generator of time evolution operators, or just generator. If it's constant, you can solve this with a matrix exponential, which is this cool thing that looks kind of like the exponential series, except you put matrices in it. For generators that aren't constant, things get complicated really quickly, especially in higher dimensions. Even really easy, simple things to write down, like squiggles on a sphere, get really, really hard to calculate exactly really quickly. So that's the point of these computer programs, these numerical integrators. If G doesn't depend on X, the generator doesn't depend on the state, then your differential equation is linear. Otherwise, it's nonlinear. Nonlinear equations get really, really complicated really quick. So if G is some nice, well-behaved function without all the stuff that physicists usually ignore and leave the math department to clean up, then it's sort of more or less constant over small time step. That vague sounding idea was actually Sophus Lee's big innovation that led to what's now called Lie groups and Lie algebras and continuous group theory. Huge volumes of material have been written about that. And yeah, it's pronounced Lie, he's Norwegian, that's how they say honey. I called it Lie the first several times. So here's where you guys might be able to find applications that I've overlooked. Very, very often in some science, X, which I'm calling just some column of numbers, bold X, it's not just some column of numbers, it describes some thing, some object or some quantity. And there will often be some laws of nature that you can cite or you can lean on. And a lot of them will take the forms of conservation laws. Like in classical mechanics, energy and momentum are constants of motion. X might wander around, but it can serve certain functions called energy and momentum. In quantum mechanics, a little more esoterically, state vectors built by unitary transformations which preserve normalization. This basically says probabilities add up to 1, otherwise they wouldn't be probabilities. In engineering and control theory, very often X is some column of numbers that describe the position of a robot space arm or controls of an aircraft or something, and they'll be constrained to some surface. The flap can only move from some range to another, or whatever. And a really fun example, if we look up Volterra models, they show up in chemistry, ecology, and economics. And there's this bizarre-looking number that's conserved in this equation that models predator and prey, or sometimes producers and consumers. So a real brief overview that physicists have to mention when you start talking about symmetry and conservation law. There's Noether's theorem. It's a really, really big deal in particle physics, but versions of it show up all over the place. And it's very hard to state precisely, and I'm sure I could do it. So the cheap version is, if a system has a continuous symmetry group, there is some conservation law. Roughly speaking, if there's some number you can change smoothly that leaves some other number unchanged, like you could change position but total energy stays the same, then there's some conservation law you could derive from a very complicated symmetry argument. And that was from the famous Göttingen school that taught Einstein math. And many numerical integrators just completely ignore this. If you look up, if you use some ODE integrator built in with whatever software you're using, or you use whatever your department wrote for you in Python, it's very likely you're going to use like a Runge-Kutta or an Adams integrator or something, and it will just completely ignore Noether's theorem. And if there's some quantity that's conserved, it won't conserve it. And a geometric integrator can be sort of broadly defined as some computer program that solves these initial value problems and tries to respect symmetry, to preserve conservation law. In my case, I had to describe these points moving around in the sphere, and it was really important for my argument that they really, really stay on the sphere. Normal integrators are terrible at that. And the one that I found is really, really good at it. So a few examples that are known. If you go talk to astronomers, especially the computational people, they'll know about a symplectic integrator. The symplectic group is a really complicated way to describe conservation energy. If you're trying to predict orbits of some things, you're never going to predict them perfectly. Computers aren't perfect. But maybe there are certain numbers where you'd really like the error to be small. So if you use a non-geometric integrator to predict an orbit, it might spiral inward or outward, and you'll predict that orbits collapse when they shouldn't. And a geometric integrator will make different errors that conserve energy or momentum. It's called a symplectic integrator. The thing I use is called a Magnus expansion, which is a really cool sounding name. It's for this guy, Wilhelm Magnus. It was designed for quantum mechanics and nuclear magnetic resonance in physics, chemistry, and medicine is where it gets used a lot. But even in quantum mechanics, most people I talked to had never heard of it. I had never heard of it, kind of by accident. And I'm convinced it's got lots of applications outside my squiggles on spheres with a good problem. It's really good at solving finite dimensional Schrodinger equations. If you have an initial value Schrodinger problem, you should really look at these Magnus integrators. So here's some actual numerical methods. The Euler method is the first one you learn in a textbook. It's terrible, but it's really simple. The idea is I'm going to advance this column of numbers, which I'm calling bold x, by some little amount, which is for no reason I can think of conventionally called h. So I want to see what's x some millisecond in the future or whatever. And this cheap way to integrate it is to just assume that g is constant and treat it like it were an integral. And that's the Euler method. And the exponential Euler method is one of the simplest geometric ones. The Euler method is horrible at preserving group symmetries. The exponential Euler method is not particularly accurate method, but it's really, really good at preserving these Lie group symmetries because it uses this thing called the exponential map. And if you want to know why that matters, you have to go talk to my advisor, Bob Gilmore, and buy his book and spend several years figuring out what he was saying. A really, really powerful method that is often the first mentioned in these fancy Magnus expansion papers I was reading is the exponential midpoint method. If you've done numerical integration, you know the midpoint method. It takes a time step, breaks it into two pieces, uses the cheapo Euler method to guess a half step ahead, then uses that to guess the next step ahead, and it does better than the Euler method. It blows up less, it's more accurate. You could make an exponential version of that, where you just replace the Euler parts of it with exponential Euler. And I use this, that's kind of my heavy-duty fallback thing, because it's really easy to code and stunningly accurate at preserving these Lie group symmetries. In my case, no matter how hideous the equation got, my points stayed on this unit sphere to within 10 to the minus 14, which was really impressive considering how crude this method was. So it's only a second-order integrator, but it's great at preserving these symmetries. So if you have a problem that has some symmetry and it's important to respect it, you might want to look this up. Or a bunch of papers that I'm going to make my last slide, part where you can write down. You better go read the whole story. So my programs, you can get one of them online now for free. You can get another one online soon as I get it uploaded and finish the instructions. I call them LinMax and StratoMax. That's acronyms. LinMax is Linear Integration by Matrix Exponentiation. And StratoMax, you don't want to know where that comes from. But they're open source software packages with a really permissive license that lets you get away with almost anything except pretending that you wrote the program. And I wrote a MATLAB version and a NumPy, SciPy, Python version, which I use in my thesis for this squiggles with spheres problem. I've got a brief example here of solving a harmonic oscillator, an area oscillator problem. And I've drawn little lines. The black line shows an exact solution. And you can't see the blue line, that's my LinMax solution, because it matches the black line so closely that it's hidden. And the red line is Runge-Kutta, which rapidly spirals inward and then unexpectedly explodes and starts giving answers that are off by 10 to the 300. And then I've drawn a phase portrait. You don't really need to know what that is, other than that if you're really into dynamical systems. There's some geometry embedded in them. And the little black dots are where the solution should be in phase space, and the little blue bullseyes are where LinMax estimated them, and it did a pretty good job. And that red mess of garbage is Runge-Kutta self-destructing. And that's the Runge-Kutta fourth order is a pretty nice, like famous, well-known, pretty stable method. And with this problem, I just blew it up real easily. Of course, I picked this problem specifically to be something where a geometric integrator, Magnus integrator would do great. So the point is, there are problems where even a perfectly good method like Runge-Kutta is horrible and will blow up your problem, and you should be using even a cheap geometric integrator. And how to know when you should even be worrying about this is, there's some symmetry or some conservation wrong, and it's important. So LinMax technically is a sixth-order Magnus expansion invented by a guy from Cambridge in 2011, and there's my website. You can download it, read the instructions. And the instructions are huge, and they include a whole lot of background. So it's written so you don't have to have a PhD in applied math to use it, or at least that was my intent. And StratoMax is really fancy. It solves stochastic differential equations, which show up in control theory and finance, and in my problem, it's to use stochastic differential equations to model noisy experiments. It uses XMID with a really not well-known method. I'm calling it the Castell-Gaines method. It's from a paper by two people called Castell and Gaines in the mid-90s. And they have this really clever technique for solving these differential equations with noise in them. Anyway, that will be online pretty soon. And here is, if you actually want to read about all this stuff, and not just a condensed 10-minute version, this is basically all the cool ideas in my programs came from these papers. And if you're at a university, you can get past paywalls, download these if you have any interest in this at all or any use for it. And then at the bottom is a shameless plug for my advisor's textbook, which actually is really good if you want to know this stuff in more depth than I've given. Anyway, I think I'm out of time. So that's nice. That's my last slide.
Sam, I think that was a great presentation on not the details of your thesis per se, but essentially how they apply to other things and how you sort of some new knowledge of how to really develop some new mathematical techniques. Next on the agenda is Michael Naguib from the Department of Material Science and Engineering.
and Drexel Nanotechnology Institute. Today I'm talking about MXene, a new family of two-dimensional material. I know that a lot of people from different backgrounds, so I need to define a few things. First, if you'd like to define what's material, if you go to Oxford Dictionary, you'll find a definition saying material is a matter from which a thing is or can be made. Actually, it doesn't have much. Let me tell you a little bit simplified explanation. It's a bunch of atoms packed in a circle. So, for example, here's a graphite, which is carbon. You see graphite everywhere in your pencil and everywhere. So it is actually a bunch of carbon atoms ordered in a certain way in layers. Also, you can have the same atoms ordered in different way and forming different crystals that has totally different properties. So the same carbon atoms, but ordered in cubic structure, are giving us diamond. And you can imagine the difference between graphite and diamond. Diamond is much more expensive, and a lot of girls like diamond, and everyone likes diamond. But also graphite is very useful for other applications. Also, we can look at materials from other perspective, from dimensionality perspective. So let's keep the graphite example. 3D layers of graphite, or several layers, are stacked on each other. If you take only single layer of the graphite or single layers of carbon, we call it graphene. It's a 2D material. So we're going from 3D to 2D. If you start to scroll one sheet of the graphene, you start to form something called carbon nanotubes. And if you crumple one piece of the graphene sheet, you form something called fluorine or buckyballs. They have the same shape as a sugar ball. So going from 3D to lower D, we are going from micron size to nano size. To let you know about nanometer size, we are talking about 1 meter consists of 1,000 million nanometers. So here's a small comparison between micron size and nano size. Look at this human hair compared to nanowire. So this human hair has a round diameter of around 60 micron, and by focusing more or by going to higher magnification, you can see here this is a nanowire of around 100 nanometer, and in the background is a hair. So there is a big difference in size from micron to nano. So back to two-dimensional materials. The best example, as I mentioned, was graphene. Graphene consists of only single atomic layer material. But actually, two-dimensional material can expand a little bit more than one atom layer. But the most important thing is you have nano size along the C direction, and you have larger or infinite size along X and Y direction. Graphene won Nobel Prize in 2010 for the groundbreaking experiment regarding two-dimensional material, graphene. So what do you need to get a Nobel Prize? Actually, all what you need to get to do is to have a Scotch tape and graphite. But reality is more complicated than that. You need to separate single layer of graphene, and you start to make devices, and you need to characterize it, and you need to get an outstanding performance, published in Science, and then you may get a Nobel Prize. So it is more complicated than just having just a piece of graphite and Scotch tape. Actually, this technique was very nice and simple, but it worked for graphene and it works for some other layer material, but it doesn't work for everything. So, because it needs to have very weak bonds between the layers to separate them mechanically with a Scotch tape as well. Actually, why graphene is interesting? Graphene has a unique morphology. They are flat, so you can make micro devices out of them. Also have very high specific surface area, around 2,600 meters squared per gram. To imagine this number, imagine that you have just 4 grams of graphene, and you can cover the entire field area of American football. So just 4 grams of material can cover all those areas. So it has a very high specific surface area. Also Also, graphene has unique behavior, ballistic conductivity, and this is actually was the reason why graphene won the Nobel Prize, because it has very high electronic conductivity. The electron can travel for very long distances without getting distracted with anything else. Also, it has very high strength. It has 200 times strong. It is 200 times stronger than structural steel. So you can. I like this schematic. You can have an elephant standing on graphene sheet on top of a pencil tip without destroying it. So graphene is very interesting, very unique. But actually, graphene is not alone, and graphene has a limited chemistry. It's just carbon, which is interesting for some application. But this limited chemistry does not allow you to do a lot of things. Also, more layered structures that contain more than one element give you more variation in the compositional variable. So you can tune properties and you can have even new properties. I'd like here to quote something from Castroneto and Novsolov. Novsolov is one of the Nobel awardees. They say that graphene is probably the most famous example, but there are numerous other examples with amazing electronic and structural properties that they need to be explored. Other two-dimensional materials, there are hexagonal chloronitride, there is transition metal oxide and hydroxide in different phase. There are also chalcopenites. Actually, most of those other two-dimensional materials, other than graphene, most of them are not electronically conductive. No one reported before on two-dimensional material of transition metal carbides or nitrides. So, here at Drexel, we work with a material called MXene. It's a layered transition metal carbide. And it actually was reinvented by our group 15 years ago, because the first time it was reported in 1960 something. But the first time it was made in fully dense material with our group 15 years ago. And max phase, the M in max phase stands for early transition metal, any of those red highlighted titanium, any of those. And A stands for A group element, any of those blue highlighted. And X stands for carbon nitrogen. And they can have chemistry of Mn plus 1 AXN. So you can have different structure, 2113 or 413. Here are some examples. There are more than 60 of different max phases. And also there are solid solutions where you can have different atoms at the M side. For example, titanium Naguib aluminum carbide, you can have different atoms at the M side. And carbon nitride, where you can have carbon and nitrogen at the X side. So considering solid solution as well, there will be much more than those 60. So if we look closely at the max phase structures, we can say that they have blocks of MX interleaved with A layer. The bond between MX here is a mixture of covalent ionic bond, where the bond between MX and A is metallic bond. So metallic bonds are a little bit weaker than covalent mixed ionic covalent bonds, but they are still strong. You cannot separate them by Scotch tape. So we were trying to separate them. So can we exfoliate max phase and form 2D layers of transition metal carbide? We proposed 2 years ago to selectively etch the A layer from the max phase because it's a little bit more reactive, and then by doing sonication, then we can separate the layers. And actually, we managed to do that by immersing just the max phase. This is titanium 3 aluminum carbide tube in hydrofluoric acid at room temperature for just 2 hours. And what hydrofluoric acid does is it does etch the A layer from the structure and replace it by OH. Then, by just doing sonication, or ultrasonication, you can start to separate the layers from each other. And we call it MXene because there is no more A element in the max phase. And we put the suffix "ene" to stress that they are very similar to it. If you look at the morphology of those particles after the HF treatment, here is the scanning electron microscope image. You can see that it has very open structure, especially when you compare it to before the treatment. It's just bulk, it's a round material. And after the treatment, it's very similar to what was reported for exfoliated graphite. So we have a material very similar to exfoliated graphite with wide variety of changing compositions. We did sonication, and then we did transmission electron microscope. Transmission electron microscope can go to much higher magnification than scanning electron microscope. And you can see here, this is a sheet of titanium. The chemical composition shows titanium, carbon, oxygen, chlorine. And I'm not sure if you can see it or not, but it's electronically transparent. You can see the carbon grade underneath, so it's very thin. And if you look at the cross-section, this is a cross-section for one of those layers. It's actually 2 layers, if you look at the domestic model. Each layer is consisting of the MXene block, which is around 5 atoms. In this case, which is titanium 3C. We can have it 2 atoms in case of titanium 2C. Sorry, 3 atoms. They were not only electronically transparent, but they were also optically transparent. This is a flake of MXene, and this is using optical microscope, transmitted, and can see that they are optically transparent. Not only 2D sheets were observed, but we also observed some scrolls. So some of the MXene sheets during sonication, they started to scroll and forming MXene scrolls. This was reported also in case of graphene, that graphene sonication started forming scrolls. Then we started to look at other max phases to make sure that we are not talking about only one phase. So we selected different max phases to cover different subgroups of max phases. And we managed to, as you see in the picture, we managed to exfoliate all of them. So also by pressing the MXene powder after the HF treatment, we were able to make thin discs of around 300 microns and they are freestanding. By measuring the resistivity and contact angle, we found that the conductivity is very similar to multi-layer graphene, and the contact angle measurement using water showed hydrophilic behavior. So graphene is hydrophobic. If you have something with, I will not say the same electronic conductivity, but close to electronic conductivity with different surface chemistry, then you can use it in different applications. Here are the potential applications for MXene as other two-dimensional material, 2D electronics like transistors, micro devices, screens, and others. Also, they can be used in composites and energy storage systems. And I'm interested more in energy storage systems and more specifically on lithium-ion batteries. So lithium-ion batteries are everywhere in your cell. I'm sure that in everyone's pocket he has a lithium-ion battery in your cell phone, on your laptop, or camera. People are trying to get more hybrid car with lithium-ion batteries. Also, lithium-ion batteries are important also not only for the portable devices, but also for energy storage systems. So right now, all over the world, people are trying to depend more on renewable energy. There's an issue for renewable energy that you have a gap between demand and supply. You may have high demand, but at that time you have shortage of supply. Or you may have high supply, but less demand. So to fill this gap, or to bridge this gap, people need to use energy storage systems to store energy at the time you have high supply, to use it when you have high demand. So how does lithium-ion battery work? It consists of cathode and anode and electrolyte. And then during dissociation, ions are going from the cathode to anode. During dissociation, ions are going back to the cathode. And you store energy in this way. The commercial batteries has cathode of lithium cobalt oxide and anodes of graphite. And most of the people use LiPF6 as electrolyte. LE side, LiPF side. I look more on the graphite anodes. There are issues with graphite anodes in lithium-ion batteries. One of the issues is safety. All of us heard about the Boeing accidents of flights, Dreamliner caught fire, and also laptop may catch fire, so be careful due to the lithium-ion battery accidents. Also lifetime, all of us are suffering from the cell phone dying, and after 5 months if you get it. Also cycling rate, you need to spend a long time to get your battery fully charged. So all of those are issues for graphite anodes and lithium-ion batteries. We try to test our material in lithium-ion batteries. Here are some results for the capacity. You can consider the capacity as the amount of gasoline you put in your car, for example. So here's V2C. 1C in cycling rate, it means you fully charge your cell in 1 hour. 10C means you fully charge your cell in 6 minutes. And we get capacity a little bit lower than what was reported for graphite, but at high cycling rate, we have higher performance than graphite. So we can cycle our material better than, at fast rates, better than graphite. More recently, all the results I was showing, it was on materials that at that stage, after the HF treatment. So we try to delaminate all the layers from each other. So by doing interpolation of something between the layer and then separating the layers more from each other. So this approach was reported before, or actually it was done by ancient Egyptians like thousands of years ago. I was trying to find a picture, I was not able, but I found a picture from Herod Temple, Mount Jerusalem. They make a hole in the stone, and they put a beam of rod, and then they put some water on the rod, and on the wood. And then the wood start to expand and separate the layers, or separate the stones from each other. Similarly, we put dimethyl sulfoxide between the layers here, and then co-integrate water, then sonication, we separate the layers from each other. And because MXene is hydrophilic, so they can form a stable suspension in water. By filtering this suspension, you can form electrodes. They are flexible. And by testing those electrodes in lithium-ion battery, we got performance of around 410 mAh in 1 hour. And 110 mAh at 36C. 36C means you fully charge your cell in 100 seconds. So imagine you fully charge your cell phone in 100 seconds. And actually this value is higher than what was reported for graphite at 1C. And graphite at such high cycling rate has zero capacity, you cannot use. In summary, by selectively etching the alien from max phase, we were able to produce a family of two-dimensional material, we call it MXene. Then now we were able to produce 7, we expect we'll be able to produce hundreds of them. The process is very simple, you can highly scale it up from grams to kilograms quantities. And we were able to make electrodes that can be cycled very fast with good capacity. At the end, I would like to thank both groups, DNI group and Max group, and founding agents, and thanks for your attention.